Hello friends, in this video I am going to explain RSA algorithm along with a solved example. So it will be very helpful to you to solve any type of example related to RSA algorithm. In this video I have explained RSA algorithm in the easiest manner possible. So watch the video till end and subscribe our channel for more such videos. So without wasting our time, let's start. Introduction to encryption. Before we get into the details of RSA, let's understand the basic concept of encryption. Encryption is a method of encoding information so that only authorized parties can access it. In other words, it keeps our data private and secure. RSA is a powerful encryption algorithm that uses prime numbers and modular arithmetic. Key generation. The first step in RSA is key generation. We need a public key for encryption and a private key for decryption. Here's how it works. Select two distinct prime numbers P and Q. Calculate n, the product of P and Q. Compute phi n, also known as Euler's toroid function, which is P-1 into Q-1. Choose an encryption key E, which is a number co-prime with phi n and less than phi of n. Calculate the decryption key D, which is the modular multiplicative inverse of E modulo phi n. Encryption process. Let's see how encryption works in RSA. Convert the message into numerical values using a mapping scheme like ASCII. Split the message into blocks, ensuring each block is smaller than n. Encrypt each block by raising it to the power of E and taking the modulo n. Decryption process. Decrypting the encrypted message is straightforward with RSA. Take each encrypted block and raise it to the power of D, modulo n. Convert the decrypted block back into their original representation. Security of RSA. The strength of RSA lies in the difficulty of factoring large numbers. Since finding the prime factor of a large number is computationally intensive, it makes RSA secure against brute force attacks. The larger the prime numbers, the stronger the encryption becomes. Applications of RSA. RSA has numerous applications beyond encryption. One significant application is digital signatures. In this case, the roles of encryption and decryption are reversed. The sender signs the message with the private key and the recipient can verify the signature using the corresponding public key. Example of RSA. Key generation. Choose two distinct prime numbers P is equal to 5 and Q is equal to 7. Calculate n is equal to P into Q, which is equal to 5 into 7, which is equal to 35. Compute phi of n, which is equal to P-1 into Q-1, that is equal to 4 into 6, which is equal to 24. Choose an encryption key E such that 1 is less than E less than phi of n and E is co-prime with phi of n. Let's choose E is equal to 5. Calculate the decryption key D, which is the modular multiplicative inverse of E modulo phi n. In this case, D is equal to phi, since phi into phi mod 24 is equal to 1. Encryption. We want to encrypt the number 12. Encrypt the number 12 using the public key E, n, and the encryption formula C is equal to m raised to E mod n. So C is equal to 12 raised to 5 mod 35, which is equal to 2. So the encrypted number is C, which is equal to 2. Decryption. To decrypt the encrypted number, we use the private key D. Decrypt the number using the private key and decryption formula m is equal to C raised to D mod n. So m is equal to 2 raised to 5 mod 35, which is equal to 12. So the decrypted number is m, which is equal to 12. So in encryption, our C is 2 and in decryption, our m is equal to 12. So decrypted number is 12 and encrypted number is 2. That's all. This is all about RSA algorithm.